Okay, so in this video, I'm just going to talk a little bit more about how to schedule with resource constraints. So as we saw last time, one of the most popular HLS scheduling algorithms, basically, which is called Zhang's scheduling algorithm, or the SDC scheduling algorithm, basically takes the problem of translating an LLVM program into a finite state machine and casts it as an integer linear programming problem. And actually, the name SDC scheduling stands for System of Difference Constraint Scheduling, because the integer linear programming problem that we come up with, if you remember from the first videos about scheduling, really is just a bunch of constraints about the order on integer variables. And that's actually an easier fragment of integer linear programming called difference logic, where really it's technically an ILP problem, an integer linear programming problem, but the constraints are so simple that all you're really doing is coming up with an order on events in time, or more precisely, coming up with an order on intervals in time, where each interval represents an operation being executed. And we basically infer a finite state machine from the results of that optimization problem or SAT problem. And this simple method can be extended to support pipelining and speculative execution, and I'll talk about that later. But today I want to talk about a more immediate problem. So the reason why difference logic was appealing to the people who created the SDC scheduling problem, or the SDC scheduling algorithm, is that actually, as we'll see on this next slide, SDC scheduling is polynomial time. So even though it's technically an integer linear programming problem, it's such an easy fragment that there's actually a sort of polynomial time graph traversal algorithm that can solve the SDC problem that Zhang's scheduling algorithm comes up with. And that's, that should raise a red flag, right? Because it's very well known that the optimal scheduling problem, coming up with a minimum latency schedule for a computation given limited resources, is NP hard. And similarly, the problem of coming up with a resource use optimal solution to a scheduling problem given a time constraint is also NP hard. So what's the catch, right? How are we solving a polynomial time problem, or an NP hard problem in polynomial time? And the catch is that we actually use a heuristic to make resource allocation decisions when there's resource conflicts. So now I want to go back to this demonstration high-level synthesis system to just show what that looks like. So to do that, we're going to take a look at another test case, which is adding numbers with resource limits. And the file that we're going to work with here is the file many adds. And it's got a pretty normal test structure, so we're going to basically load this module and get the function for the module, and schedule it and turn it into an STG and then compile that into Verilog. But the first thing I want to show is, so our many adds program, well, first let's take a look at it. So in the same directory that we had single store, we have many adds. And the program takes in a bunch of arguments, A, B, C, and D, and it sets D equal to the sum of A, B, and C. So we've got two adds, right? This first add and this second add. And we're going to say in our hardware constraints that actually, even though this program has to do two additions, we're only going to have one adder. So we've got to do two additions using only one adder functional unit. And the scheduler needs to be able to deal with that. And, well, if we run this program, so let's just run that one test case. So it passes the test, and up here, what you'll see in the state machine is we have a bunch of different states, 0, 1, 2, 3, 4, and 5. And again, there's no control flow in the program, so the state transitions are pretty boring. But what you'll see is that the first add in the program, and maybe I'll just open the LLVM version of the program, so manyadds.ll. So here's the translation of the C program into LLVM. And basically, we load two of the values A and B, and then we add A and B, and then we load C, and we add C to the sum of A and B, and then we store that result back, and then we're done. So loads take a cycle to complete. So in the 0th state, we start the loads of 1, 2, and 4. Then we complete 1, 2, and 4 in state 1, and as we complete them, we add 1 and 2 together, but we don't add 4 to that sum until the second state. Now, so notice the two adds in the program have been split up into two different states. And notice that, for example, if we were to remove this resource limit that the add op takes one cycle, or excuse me, that we only have one adder. Sorry, adds take 0 cycles. But if we remove the resource limit that we only have one adder, recompile and rerun the test, we'll see something very different. So, well, this is going to take a second to compile. Waiting. Wow, this file takes a little bit of time. That's C++ for you. Okay, and we recompile. What we see is now, in state 1, we add 3 and we add 4, and we add 3 and 4 together in the same state. Whereas in the resource-constrained version, the adds are split up across 2 states. And to split up the adds across 2 states, so if you look at the resource or the constraints that go into the scheduler, what you'll see is that the different add operations have all the normal constraints about having to proceed in basic blocks. And then there's this extra strict constraint, which says that one of the adds, add 1, 4, has to come before, or has to come after add 1, 2. And basically what that constraint is saying is the 2 different add instructions, which are represented by those variables, have to start in different states. They have to be split up. Or they have to execute in different states in this case because add is combinational. And the order in which the adds are chosen to start is arbitrary. You can pick it to be whatever you want. And in this problem, it doesn't matter. But in some problems, ordering can make a big difference for performance. And the way you choose to order them before you feed constraints to the scheduler can have huge effects on performance in more complicated programs. So that ordering heuristic lets us split operations up across states and avoid resource conflicts where we've scheduled too many of a type of operation in one state. And it's a blessing because it creates a polynomial time problem, but it's a curse because picking a bad resource ordering in problems that are not as symmetrical as this one can lead to very bad performance. So it's something to keep in mind with this scheduling algorithm, and it's the way that we get an easy problem at the expense of potentially a bad solution.